Hello, in today's video I'm going to try and explain one of the quantum computing concepts known as quantum teleportation. In quantum teleportation, you might think it's a teleportation of, in sci-fi, where you're moving one place, teleporting from one place to another. However, it's not the case. In this case, we're teleporting information from one qubit to another qubit. And in this process, one of the qubits information will be corrupted as its information is being teleported to a different qubit. And this ensures that we're following the no cloning theorem, meaning that we're not cloning a qubit, we're just teleporting it. And to show the quantum circuit, we have qubit A trying to send a message to qubit B. It's trying to send the information in qubit Q and teleport to qubit B. And we'll denote the information in qubit Q with ket psi being an arbitrary quantum vector state. And A and B are entangled and are represented by the Bell state ket phi plus. And when they're entangled or correlated, and that means these two qubits are not independent in their probabilistic states, they're dependent. And to further show, we have an arbitrary vector ket psi equaling alpha ket 0 plus beta ket 1. And we have our Bell state, which is shown here. And yeah, as I was saying earlier, when two qubits are correlated, that means it is basically impossible to, like in this case right here, it's impossible to get two single system qubits and have their overall state of the two qubits end up like this if they're independent, because that is impossible to reach. There's no two single system qubits that can be tensored in this quantum vector state right here. And then continuing, we can solve for an initial vector state of the system with denoting it by ket pi 0, which is equal to ket psi tensor product ket phi plus, and that is equal to the following expression here as we substitute those vectors in, and then we can simplify further to this expression right here. Now we will be trying to solve for ket pi 1, which is solved for by taking the C NOT gate and applying it to qubits Q and A. I have the matrix here, you need to reference it. This is essentially saying if qubit Q is 0, do nothing to qubit A. But if qubit Q is 1, invert qubit A, and which is the case where my laser pointer is here, it's going to invert this 0 to a 1 and invert this 1 to a 0, as represented here, as this 0 from above is now 1, and that 1 is now a 0, due to the state of qubit Q being in 1. Now we'll solve for ket pi 2 by applying the Hadamard gate to ket pi 1, and that is expression here, denoted by ket pi 2, and also right here we have the Hadamard gate in this orange box, you need to reference it. And this expression can be further rearranged and simplified to this. And right here we have 4 outcomes based on qubits Q and A, where they are 0, 0, 0, 1, 1, 0, and 1, 1. And each of these outcomes have a probability associated with it, being 1/4 for each one, which can be shown by taking the magnitude of each of those components or coefficient of each each component of the vector, which in this case is for, let's just say this quantum, or for this vector state here, the probability will be 1/4, which can be shown by taking the magnitude of the component sorry about my horrendous handwriting, and taking the magnitude of that and squaring it, which is equal to magnitude of absolute value of a squared plus, or magnitude of a squared plus magnitude of b squared. These are complex numbers, and we know a squared plus b squared is 1 because by definition of a quantum vector state, they have to equal 1. We're given that ket psi is equal to alpha ket 0 plus beta ket 1, meaning that has to be 1, which equals 1/4. So there's a 1/4 outcome of qubits Q and A measuring to be 0, 0. And to the next slide. And these are the 4 outcomes based on the qubits being for Q and A to be 0, 0, 0, 1, 1, 0, and 1, 1. And in those cases, if it's ket 0, 0, we'll have our desired arbitrary vector ket psi being in qubit B. But in this case, the coefficients are switched, and in this case, it's negative, beta is negative, and in this case, beta is negative, and and in a wrong spot in the column vector. So to fix this, when we measure the classical states of Q and A, which is what these two boxes are doing, if we say if A is equal to 1, we'll apply a poly X gate, which is in this orange box right here. Actually, if it is in ket 0, 0, where Q is 0 and A is 0, their metric is 0, we'll just play the identity matrix and not do anything to this vector. But if we get A to be 1 and Q to be 0, we'll apply the poly X gate, which will basically switch the components of the vector. And then if Q is 1 and A is 0, we'll apply the poly Z gate, which multiplies -1 to the second component of the vector. And in the case that both Q and A are equal to 1, we'll apply the poly X gate and then poly Z gate in that order. And then we are left with qubit B being the original vector state that was Q, and is now alpha ket 0 plus beta ket 1, and that is the vector state of qubit B. However, by these operations and measuring qubit Q, we are collapsing its superstition, meaning we are corrupting the quantum state vector, because when you measure it, it corrupts it, and therefore B isn't cloning Q, as Q is teleporting information to B, and information in Q is just being corrupted. And it also should be noted, something similar happens with A, and then A and B are no longer entangled after this whole operation. And now is a good time to run some example code to show how this works in code form. So right now I'm going to explain the Qiskit code for this quantum circuit showing quantum teleportation. So right here I'm importing all the libraries, and then I'm making qubit to represent Q, qubit Q, and ebit 0 to represent qubit A, and ebit 1 to represent B. And we're calling these ebit because they're entangled bits. And we have classical bit A and B to represent the measured states of Q. These are classical states to measure the measured states to store the measured states of Q and A. And right here we're just making the quantum circuit, and then here we're making the Bell state with ebit 0 and ebit 1 by applying a Hadamard gate and a controlled NOT gate, which is how you make a Bell state. And then we're going to apply the quantum circuit that was shown earlier by applying a controlled NOT gate to Q and A, and then Hadamard gate to qubit Q. And then we're going to measure the two and apply them qubit A to qubit Q and qubit A, and we're going to apply them to the classical states when we measure them. And then if we get a measured state of 1 for classical bit A, then we will apply the poly X gate, and if we get a classical state 1 for the classical B gate, or B state, we will apply the poly Z gate. And then this is shown through the diagram again. So right here we have making the Bell state, then applying the control NOT gate, Hadamard gate, then measuring the two quantum states, and saying if A is 1, then apply X, and if Q is 1, then apply Z. And these solid, more thicker lines represent the classical states, as opposed to thin qubit lines. These classical bits are represented by thicker lines. And right here we're making a U gate that makes a random quantum state vector, as this quantum circuit should work with any arbitrary quantum state vector that can exist. So we're just making a random one right here, and then we're applying that to our initial 0, like the default gate or default vector for every qubit is ket 0. So we are going to test this quantum circuit and then apply the random gate to qubit, which is multiplying the matrix right here to qubit ket 0 to get a random state for qubit Q. Then we're going to run the circuit, and then we're going to inverse the result of ebit 1 with we're going to apply the inverse of random gate to ebit 1 and take our result as the measured state of ebit 1, which is qubit B. And this is just drawn out so you can see here. And then right here I'll just explain. So the 0 on the leftmost right here represents qubit B, then Q and A. And B is 0 for all of them because we are applying a matrix right here, and we're applying the U gate right here, and we're teleporting Q to B, and then we're applying the inverse. And we know it teleported because Q to B got inverse to this, and it's always 0 now. And as shown here, all outcomes of measured state B is always 0, meaning it got teleported. And then right now we're just left with these 4 outcomes, which are, as shown earlier, where we had the 25% chance for each outcome. This is what that represents, where we have qubits Q and A being 0, 0, 0, 1, 1, 0, and 1, 1. And yeah, this is just the code that shows that we're actually teleporting Q to B. And this is proof by the graph right here. Okay, so that was quantum teleportation, and that was like a overview of the math and how the basics of it work. So for our next video, it's going to be more of an electrical video where I'm going to be building a voltage multiplier, and I just got my diodes and capacitors in, so also I got my transformer as well. So we're making a voltage multiplier that should hopefully give us an arc of 100 kilovolts for our next video, and that might come out in a week or 2. And you also, one other project that's in a work in progress right now is the acoustic levitator, so that might also come out in a week or 2. So stay tuned for those videos.